So what winds up happening, there shouldn't, if we just look at electromagnetic force, nuclei shouldn't exist, at least not larger than hydrogen, right? Because what do you get when you get an atom larger than hydrogen? What's in the nucleus? Neutrons and protons. Protons are all positively charged, right? Which means they should repel each other. So if you only look at charges, the nuclei shouldn't exist because we're taking these charges that repel each other and we're putting them really, really close together. Thing is, once you get close enough, these other two forces kind of take over. They become more significant than just the charges repelling each other. And those two forces are the strong and weak nuclear force. They're named the strong and weak nuclear force because they're basically what's responsible for holding a nucleus together. However, what eventually starts happening, so they started figuring out about strong and weak nuclear force in the late 1800s. A scientist named Becquerel basically he was measuring these X-rays that were given off by various minerals. They didn't know what was causing this light to be emitted from certain minerals. It wasn't like it was just glowing when they shine light on it, like fluorescence, like we've talked about before, like emission spectrum. It basically would just be constantly giving off the low levels of light, really high energy light. And so they called that phosphorescence, and they didn't know what caused it at first. But basically, anything that kind of glows in the dark is mostly a process of phosphorescence. But they couldn't come up with a reason why these minerals would give off phosphorescence. Because some things like glow in the dark soccer balls are like the little. Anybody else grow up with those little glowing stars on your ceiling of your bedroom? Those you have to shine light on them for them to glow, right? You shine light on them, and then when you turn off the lights, then they glow for a little while and they get dimmer and dimmer. That process is called phosphorescence, and because it's really similar to fluorescence. So basically, what happens is you wind up if you promote an electron from the ground state up to a higher energy state, if it falls right back down, it gives off light that's the same wavelength as the light that was absorbed. And so that's kind of like the flame tests that we did when we were calculating those energies earlier in the quarter, right? But there's a possibility that when you do that, that's what's called intersystem crossing, which basically is the spin on the electron flips. And if you're two electron states, if you start here and you promote an electron up to here, one spin up, one spin down. If it falls right back down, that's fluorescence. However, there's actually slightly lower energy state if we flip this. If we flip the spin so that they both match, they both have the same spin, then you can't just have the electron fall back down, because then we'd be putting two electrons with the same spin in the same orbital. If you remember your quantum, we can't do that. We're not allowed to have two electrons with the same set of quantum numbers, right? And so that's what slows down the process in phosphorescence, is basically in order for it to go from this lower energy state back to ground state, it has to flip the electron spin and then it can fall back down. And so they're starting to figure out some of this stuff. They didn't really have the understanding of quantum at this point, but they knew that they started to be able to measure X-rays. And so the way they originally figured out this could happen, this figure right here, was actually because Becquerel's students gave him a paperweight that was a mineral made out of uranium. And he used it as a paperweight, and he put it on top of an X-ray film. They were starting to discover how that they could develop film by shining X-rays on it, just like X-rays like you get taken off if you break a bone. And so he put this rock on top of this X-ray film, and then noticed that it started developing it when it had never been exposed to any X-rays. They thought. Turns out that was the uranium giving off electrons. And so he wound up kind of going a completely different direction with this, and wound up studying the uranium instead of studying just the X-rays. Asen? Yeah, they didn't know what radioactivity was at this point. It was kind of like the Romans, lining their aqueducts with lead. We know now that that's a really bad thing in terms of, chronic lead exposure. We know now that exposure to uranium is a pretty bad thing on an everyday basis, but they didn't know then. It was just this cool, weird rock that was really, really uncommon. They knew what uranium was, but they didn't realize it was radioactive. It is rare, but there are veins of it that it's present more or less the same amounts worldwide, but there are certain areas in the Earth's crust where you can find like veins of uranium ore. For the most part, though, when they mine uranium these days, they basically just go through just chunks of rock and they pull little bits of uranium out of pretty much all types of rock. There's not really any one. The areas where they mine uranium the most now are areas where people don't care about having a mine nearby where the land is cheap. And so it's not like the way they used to do gold mining, where you would find a gold deposit and you would follow the gold veins and dig out all the gold you could get. Now it's basically they just process all this rock and they remove all the valuable stuff from it. It's more like a pit mine. And you can find it in low levels, close to the same levels all over the place. But that's why it made it such a good present for this professor, is because it was a really uncommon ore. They just discovered that uranium existed, and then they found an ore made out of uranium, so they gave it as a gift. In fact, one of Becquerel's students was Marie Curie. And the way that they originally got their uranium samples was they would literally get, metric tons of gravel delivered from certain mines in Africa. And they would basically go through the gravel by hand and they would find chunks of uranium ore mixed in with all the other rocks. So that one just happened to be a particularly large one, which is probably why it got gifted. So everybody's heard of Marie Curie. Have I talked about Marie Curie yet? A little bit, yeah. About her daughters. She died fairly young by our standards. She died in her 60s and she looked much older by our standards, but it's difficult to say how much of that was just the time and how much of that was her genetics and how much of it was radiation exposure. But she did eventually die due to radiation poisoning, but it was not until her 60s. Her husband did die very young, which is probably why he's not in this picture. He was probably already dead. I think he died in 1906. Yeah, he got hit by a horse-drawn cart in Paris. Just crossing the street. Didn't look both ways. Got run over by a cart. And then Eve and Irene were her daughters. I believe it's Irene was the one who shares Marie Curie's second Nobel Prize with her mom. And Eve was the one who was a fighter for the French resistance in World War II. So a journalist who then went on to marry one of the people that was instrumental in founding the United Nations post World War II, who was given a Nobel Peace Prize. So Eve was the only one in her family, including her husband, her sister, her mom, and her dad, who didn't have a Nobel Prize. All she did was fight in the French resistance. So very interesting family. One of those, it'd be really interesting to be able to have dinner with them as a family. Lots of interesting experiences. One of the earliest uses that they found for these radioactive particles was actually making glow-in-the-dark watch faces. They actually used to paint the watch faces with iridium. Yeah. Their jaws all fell off. Yeah, they basically developed massive tumors all over their faces. So they would actually paint these watch faces by hand. And not iridium, it was radium. So there's a really good book that got turned into a play called Radium Girls, about the women who actually worked in these factories And in order to be able to paint these really fine details on the watch faces for the aviators in World War I, and World War II, they would lick the tips of their brushes, their paint brushes, to try and get a really fine point on it. And so they were basically ingesting radium constantly, just by working in these factories. And so there was a big issue, obviously, with radiation poisoning and developing all these other health concerns as a result of that, you know, from leukemia to, yeah, their whole jaw would have to be amputated sometimes.
How much protection do like mining need nowadays, like mining uranium?
So uranium is we're going to talk about types of radiation here in a few minutes, but uranium is actually what's called an alpha emitter, which means it only gives off alpha particles. And alpha particles are really damaging if they come into contact with your skin or your body, but they don't have very high penetrating power, is what it's called. Basically, something as thin as a sheet of paper can stop them from damaging your skin. So depending on the type of radiation you're being exposed to, you have different levels of precautions. And alpha emitters in particular are some of the easiest to sort of counteract. Anya?
Do you know how radiation creates tumors? Or does it just
For the most part, it breaks apart your DNA. It takes some of your DNA. If it happens to hit your DNA, and it can basically take, say, a T. DNA is all made up of A's, C's, T's, and G's. I think T in particular is susceptible because if you have two T's in a row next to each other, if it gets hit with a particular type of radiation or high enough energy, those two T's can kind of fuse together to make something that DNA polymerase or RNA transcriptase can't recognize. And it basically causes genetic mutations. And the most common way that genetic mutations manifest, if they cause a notable effect at all, most of those are going to be in the form of a tumor. So it's basically just like most causes of cancer are as a result of genetic mutations. And so it's literally what the radiation does is it just breaks apart your DNA and then your DNA gets put back together wrong. It is. And that, if you study molecular biology, you spend a whole bunch of time on transcription and translation, including how genetic mutations happen. Because it turns out our cells actually have a defense for that. They basically, when it can recognize a part of your DNA that's been mutated, it basically goes in and chops out that chunk and rewrites it. But it doesn't always capture that before it gets incorporated into your larger DNA structure, and sometimes that's what causes cancers. Right, so one of the things that Marie Curie won her first Nobel Prize for was she determined that only certain elements and only certain isotopes of those elements actually gave off this radiation. So we hear the term radiation now, and we think of radioactivity because they used to think it was caused by the same thing, but technically radiation just means light. But the problem is when you have some of these radioactive decays going on, the light that's given off, it's really, really high energy. Like we think about UV as being bad for your skin and causing cancer. X-rays and gamma rays are way higher energy than that. And so they just kind of lumped it all together and said, these materials are giving off radiation, this high energy radiation. And so they kind of caused it to be lumped together. So the more accurate term is radioactivity, because it's actually the activity of the nucleus that gives off the radiation. And both of them together, both of those aspects of it are dangerous, but they're always linked together. And then, so that's actually what Marie Curie won her Nobel Prize in Physics for. She won her Nobel Prize in Chemistry for actually finding a bunch and discovering a bunch of these elements. So they knew about uranium, but then she started going through all of these radioactive minerals and started trying to characterize all the different elements that were present. And she found some that nobody had ever discovered before, like radium, that's actually what that color green on watch faces used to be made from your radium. And if you have really old, like I have my grandfather was a navigator in the Air Force in the Korean War. And I have his aviator's watch that still glows green really faintly. Basically it dies off as it goes on, but you can still see glow a little bit in the dark, not bright like this. But that is what they would use was the radium here. And then polonium was named for Poland because Marie Curie was Polish. Even though she's known as Madame Curie, or you think she did all of her research in France and then left from France for the US when the Nazis invaded France. But she originally came from Poland. And then left Poland because women weren't allowed to study at the time, weren't allowed to go to university. But France, being a little bit more progressive at the time, allowed women to go to university. Even France didn't allow women to go to graduate school. After you finished a bachelor's degree, you had to be done. But she was able to find, I don't think it was Becquerel. I'm trying to think of who was her advisor, but it might have been Becquerel. She found an advisor willing to bring her on, recognized how hard she worked and how smart she was, and brought her on to go to graduate school, where she met her husband. And she was the one who renamed it Radioactivity. This is the one that's gonna make funny noises as I go. So basically what radioactivity is, what she discovered was that sometimes those strong and weak nuclear forces kind of fall apart a little bit. Sometimes the strong nuclear force was responsible for holding nuclei together, but if you get the wrong ratio of protons and neutrons, or if you get nuclei that are too big, the strong nuclear force isn't enough to keep the nucleus stuck together anymore, and it basically falls apart as a result of the weak nuclear force and electromagnetism. Right? So what actually happens is your nucleus just gets smaller. When you have especially if it's an alpha particle, what winds up happening is you just wind up with little bits of the nucleus flying off into space. Sometimes it can be even bigger than that and go through what's called fission, where the whole thing basically flies apart into chunks. So for instance, one of the examples we look at is uranium-235. If you hit that with a neutron, so mass of 1, but no charge to it. So uranium's 92. So 92 protons, to remind us how this notation works. This number is your number of protons. This is your mass number, your protons plus neutrons. So a single neutron by itself has 0 protons, but it has a mass of 1. If you launch a neutron into uranium-235 and get it stuck into the nucleus, for a split second, it'll make uranium-236. But uranium-236 is so unstable that it immediately breaks apart. And when it does that, you wind up with, I'm sure I have it in the slides here further along. Basically, you wind up with 2 big chunks. You basically wind up with your nucleus splitting into 2 chunks, and then you wind up with a couple of extra neutrons floating around. I want to say it's like zirconium and something else. We'll talk about that reaction in more detail. Basically, you get this giant uranium nucleus fragmenting. And when it fragments, it gives off a whole bunch of energy. And that energy is what was causing that high energy light, those X-rays and gamma rays, were a result of the nucleus just falling apart and giving off all this energy at once. Right? And so that process is called fission. Fission just means splitting into pieces. All right, and so I guess technically we should define nuclear reaction. A nuclear reaction is any time you wind up with a nucleus that changes composition in some way. So it can be something like this process right here. It can be something like, that'd be an example of something that's more like a fusion reaction. Or it can be this splitting into pieces. And again, I can't remember off the top of my head what it splits into, but it basically splits almost evenly into two different pieces. Did we talk about this on the midterm? I don't think so.
The midterm.
Oh, it was the bonus question. Yes, you're right. And in fact, it was this reaction. It said, and it just said gives off this much energy, and then just had you do some energy calculations.
I think it made krypton and
That would make sense. I kept wanting to say zirconium, but krypton makes more sense. Krypton and whatever is left, 92 minus 36.
140.
Yeah, I think it winds up making something like that. Anyway, it's on one of these slides coming up. The other way that we can have these things happen, if it's not a fission reaction where you get something big splitting into pieces, you can actually get two small somethings fusing in together to become something larger. So this is a different type of fusion than something freezing. Remember, we use that same term fusion for going through a phase change. We could say that, ice freezes. We also called that fusion. That's a different use for the word fusion. In this case, nuclear fusion that does occur naturally. It happens when you smash two nuclei together and make something bigger. Right, so that's one of the ways that we discover new elements too, is we use particle accelerators. It doesn't have to be gravity, but it happens naturally. Can anybody think of where fusion reactions happen naturally?
The sun.
The sun. Basically, the whole reason that the sun shines is because the gravity is smashing together helium and hydrogen nuclei to make larger elements. And that's the fact that elements exist that are bigger than hydrogen, helium, and lithium in our solar system tells us that we're a second generation solar system. That our star system must have been the result of a previous star system. We know that because we see so many of those elements on the periodic table that are heavier than iron. Anything heavier than iron has to happen as a result of a supernova. Basically, stars will keep making things bigger and going through fusion reactions until you get to iron. Once you get to iron, iron is the most stable nucleus that you can have. So if anything exists past iron, it's because of a previous supernova, which is kind of cool. All right, so I mentioned that there's different types of nuclear reactions as well, even within fission. Fission and fusion that's our biggest difference. But there are other types of reactions that can happen that are considered types of fission. Basically, they're anything that's not fusion winds up being classified as fission. And and I have a whole slide on each of these, so don't worry too much about getting all these written down right now. But alpha particles were some of the first ones that were discovered. Those are the ones that uranium gives off on its own. But then there's also these other types of nuclear decay called beta particles. And then there's positrons, which is actually antimatter. So it turns out some unstable nuclei actually give off antimatter in small amounts. And then there's electron capture. Is basically if you get an electron close enough to a nucleus, it can kind of get absorbed into the nucleus. And it converts a proton into a neutron. You can think of it like a negative sticking to a positive and canceling it out. And so they call that process electron capture. And then this gets classified as a different thing, but really all of these gamma rays, X-rays, all this high energy light that comes with these is really sort of a side effect of all these other processes. It turns out each of these different types of fission reactions, they happen because they're going downhill in energy for the most part, which means it has to release energy to the surroundings in order to do that. And we're talking about an amount of energy that's so high that it doesn't just give it off as heat. Some of these nuclear reactions will give off heat as well, which is how nuclear reactors work. But they give off so much energy so quickly that they basically, as a side effect, give off this really high energy radiation at the same time. So gamma rays is kind of like the generic term for any light that's released as a result of a nuclear reaction. But it's really any sort of photon that gets produced as this process gets categorized the same way. And represented with this gamma symbol. All right, so let's talk about these different types in order. So I mentioned uranium. Uranium in particular is the most common. It was historically the one that was first discovered to do this. So it's one gets used as the example, but lots of different heavy metals are alpha emitters. And what that really means is if you have uranium, and I'll write the protons on here as well, there's some finite chance. If you have a uranium-238 atom, at any given time, there's a finite chance it'll spontaneously split and turn into an alpha particle, which has a mass of 4 with two protons, and whatever's left over. So basically, you just break off this little particle that's got 2 protons and 2 neutrons together, and then that leaves us with thorium number 90. And then since we took away 4 of the mass numbers to make the alpha particle, we take away a 4 here as well. So the way we balance nuclear reactions is a little bit different, because the way we've always balanced reactions is just make sure you have the same number of atoms on both sides, right? Make sure your oxygens match up. Nuclear reactions, that's no longer true. We no longer have uranium anymore. Now we have thorium. But if you look at the total number of protons, they still add up to 92. We just broke this little chunk off of our uranium nucleus, and we made something a little bit more stable. And so sometimes they show it as a helium nucleus, because helium normally has a mass number of 4. So this actually is a helium nucleus as well. A lot of times we see it represented with an alpha symbol, but sometimes the way it is on the slides as just a helium nucleus.
Oh, I see.
It's basically because it's indicating that it came from a nuclear process. So it's just part of like the reading for context. If we were just talking about doing like electron configuration for helium, we would never represent it with an alpha symbol. We only use the alpha symbol when it's a helium nucleus that came from another nucleus. So this is the process that naturally happens with uranium-238. Uranium-238 is present naturally all over the world. This process gives away a ton of energy when it does this as well, in the form of light and heat. So basically, this is actually the way that nuclear power plants work, is it takes a normal isotope of something that naturally occurs in the Earth's crust, and then basically uses it to boil water. 9 out of 10 times, if you look at something that's generating electricity, it's generating electricity by boiling water and using the steam to spin a turbine. That turbine's attached to a magnet inside a coil of wire, which drives a current. So basically, natural gas reactors, coal power plants, nuclear power plants, hydroelectric dams. Solar is about the only one that doesn't do that. But there are some types of solar power plants that actually just use big mirrors to boil water and spin a turbine as well. At its most basic, that's sort of like the simplest way you can make a power plant to generate electricity is make steam, use steam to spin a turbine. However, that makes those power plants make thorium as a byproduct as well. So everybody's heard of nuclear waste and how dangerous it is. Well, it's because nuclear waste is still radioactive material. It's just not as radioactive as it was. So it's actually led to a new technology they call breeder reactors, or second generation reactors, where you take your nuclear waste, the thorium in this case, and you make another power plant that is built to run on thorium instead of being built to run on uranium. So you effectively turn your waste from one nuclear power plant into the fuel for the next nuclear power plant. So what does thorium make? That's exactly where we're going to go next. It's also an alpha emitter. So if thorium is also an alpha emitter, what will it turn into? It's going to make another alpha particle. Yeah, check on the periodic table. Thorium is 90, so it's going to turn from thorium into radium. And it's going to be 230. So this is what's called a decay series. It actually will continue because radium, like we were just talking about, uranium or radium is also radioactive, right? It's also an alpha emitter. Radium will then go on and turn on to radon. So who's here heard of radon as a gas?
Yeah.
What have you heard about it? Just of it, that it's bad? We have a lot in Kingsbury. You have a lot any place where you don't have a high water content in your soil or where you have lots of basements. Because basically uranium is present in all places on the planet, basically in small amounts. And when uranium breaks down, it first turns into thorium, which then turns into radon. And so it goes from being a mineral to being a gas. Because uranium is present as uranium ores, usually uranium oxides. Thorium can still be a thorium oxide. But once it goes from thorium to radon, radon's a noble gas. And radon doesn't want to make a compound anymore. It wants to just be a gas. So basically you get these minerals that just sort of crumble and release radon. So it's really common in mountainous areas because we have a lot of exposure to granite. Granite in particular allows radon to move through it pretty well. And so since we're built on granite here, we have a fair bit of radon present in especially in basements. It tends to accumulate in basements because it's heavier than air. So basically in any place that has basements, in the Midwest and stuff too, they also have radon problems. They don't produce radon as fast as we do because they're not built on granite, but it still kind of pools and accumulates in basements. So once you make radium turns to radon, radon turns to polonium, polonium then turns into lead. And that's actually where it ends. So basically we'll go through this decay series where you wind up with lead at the end. In particular, so if we keep following this through, it's going to be radium turns to radon, which is going to be 226, which is going to turn into polonium, 222, which turns into lead at 218. So basically, each one of these steps is also going to give off an alpha particle. So this is actually one of the ways that we can determine how old our solar system is, because there's nothing that's currently making uranium. Uranium-238 is naturally unstable. It naturally goes through this process. The fact that uranium exists at all, it's like I said before, is because it's a leftover from a supernova. Well, if you know that uranium turns into lead eventually, if you can find a rock like a meteorite that has some uranium in it, it's a pretty good bet that that uranium has been decaying since the last supernova that took place before our solar system formed. And you can actually look at the ratio of uranium-238 to lead-218 to determine how much of the uranium has broken down since that happened. And you can look at the time, you can calculate the time that must have elapsed to go from uranium-238 to lead-218. So that's actually how we date our solar system, is not just in terms of looking at the sun. It's by looking at uranium to lead ratios in certain minerals. Yeah.
It's constant, tank. We have like a limited amount during.
Unless we make more, we can make more. It just takes a lot of energy. But yeah, the good thing is this process has a half-life of about 4.5 billion years. Meaning after about 4.5 billion years, you'll have roughly half the uranium you started with. And our solar system is only about 4.5, 5 billion years old. So we still have a lot of the uranium that initially started in our solar system. But it is technically a finite resource. It's not technically a renewable resource. But realistically it is, because, I mean, on the time, it's all going to be used up in another, well, that's not how the kinetics works. But in another 10 billion years, we'll probably run out of uranium, that usable uranium, because it'll just keep getting cut in half every 4.5 billion years. I don't think humanity is planning ahead for more than, I don't know, depending on who you ask, the next couple of weeks to next 100 years. So it seems unlikely we will actually ever run out of uranium. Asim?
That much uranium.
It does. You don't actually need that much uranium. Nuclear power plants are really, really energy efficient because they produce a ton of electricity and they scale up really, really well. Basically, you can replace almost every coal and natural gas power plant in the United States with about 5 nuclear power plants. We could phase out about 500 coal and natural gas power plants and make about 5 nuclear power plants. The problem with that, though, the reason that we haven't leaned into nuclear to kind of get away from fossil fuels, is basically there's about a 20-year turnaround before you actually start getting a return on investment. And since most of the power plants in the United States are not owned by the government, they're owned by corporations that don't want to wait 20 years to see a return on investment. We've kind of passed the window where that's going to be useful, because now solar and wind are making such headway that it makes more sense to switch to solar and wind. If we built a whole bunch of nuclear power plants in the 80s, we could be completely off of fossil fuels by now. But in the 80s, nuclear was still a 4-letter word, because of Chernobyl and 3 Mile Island.
Are they making a bunch of like smaller nuclear power plants?
There's some, in some countries, yes. I don't think they're doing much in the US. I don't think there's been construction on a new nuclear power plant in the US since the 80s. But I could be wrong on that. It's been a while since I looked at the numbers. Zach? What about fusion? Fusion is sort of a holy grail problem. Like, that's like, if we could get nuclear fusion reactors to work sustainably, we can get fusion reactions to happen. And they give off a ton of energy really, really fast. We just can't do it in a way that we can capture that energy. We're really good at making fusion bombs, not so much fusion power plants. We're really good at getting it to release all that energy at once, and then it's all gone. If we could get fusion reactions to work, though, sustainably in a power plant setting, it would be game changing. Electricity would be pennies on the dollar compared to any other source. And it doesn't produce nuclear waste as a byproduct. It produces stuff that's pretty easy to use, capture, and that's not radioactive anymore once you do that. But the running joke is that fusion is about 20 years away and has been for the last 70 years. Since about the 60s, the early 60s, they said, oh, we're about 20 years away from being able to make a fusion power plant. And it's always been 20 years away, for my entire life. Until about 10 years ago, when I think it was Northrop Grumman, released a press statement saying that now we're only 5 years away. But that was 10 years ago. So who knows? but it would be a really, really big deal. And it would make electricity so cheap and plentiful that it would actually eliminate a lot of scarcity in terms of drinking water as well. Because when electricity is so cheap, you can just build desalination plants wherever you need water. So any country with access to the coastline, landlocked countries would still be in trouble. But if you have access to coastline, you have as much water as you need, basically. Plus, it would also make it so that we could go anywhere in the solar system. Everywhere in the solar system has hydrogen. And if you have hydrogen, you can turn it into a fusion reaction, in theory, if we could make this work. So it would actually allow us to explore the solar system and colonize the solar system a lot more thoroughly and sustainably if we could get that to work, because we could just build a power plant as soon as we landed on Mars and have no scarcity of electricity once we got there. And if with enough electricity, you can do anything. All right. So more details on that on Wednesday and Thursday, or on Friday. We'll talk more about sort of the engineering aspect to it. Let's talk about some other types. The second most common type of nuclear decay, of nuclear reaction, is beta particle decay. So alpha, beta, we're just using Greek letters and going in order at this point, right? A beta particle is basically an electron. But just like before, we use the alpha symbol to indicate it's a helium nucleus, but it came from a nucleus. We use a beta symbol instead of just calling it electron to indicate that it didn't come from the valence shell or anything like that. It actually came from the nucleus. So a beta particle is basically, if you can kind of think of, and this isn't energetically what happens, and it's more complicated, but you can kind of think of a neutron as being a proton that has an electron stuck to it. Right? And so it has a mass like a proton, but it has zero charge because your proton and your electron are canceling each other out. But occasionally you can basically shake that extra electron off of a neutron, and it turns a neutron into a proton.
Is this the reaction that we use for carbon?
Exactly. So up in the upper atmosphere, CO2 gets hit with radiation from the sun that's high enough energy that it actually turns, I'm sorry, no, it's nitrogen. It turns nitrogen into carbon-14 in the upper atmosphere. And that carbon-14 then gets incorporated into CO2 and then winds up being incorporated into sugars and into plant membranes and into basically everything living has a certain amount of carbon-14 in it. So, and when carbon-14 though eventually does break down, it gives off a beta particle. All right, so what this is really going to look like is if you've got carbon-14, when it turns into a beta particle, the beta particle doesn't have a neutron. It's got a mass of 0 because it's like an electron. It is an electron. And so sometimes we actually, to make it more similar to what we've done in the past, you can write the -1 as the charge because it is charged. But in terms of adding up these and balancing these reactions, sometimes it makes more sense to put a -1 right there. And then what you wind up with next to that is the mass didn't change. Our nucleus is still the same mass. But now we have one extra proton. Something that was a neutron turned into a proton, and it gives off an electron as part of that process. You basically fling an electron off into space, and now you have one more proton than you did before. But the mass is the same. And so when you look at these nuclear reactions, when we talk about balancing them, you basically just need to make sure that your number of protons add up. 7 plus -1 adds up to 6. And you make sure that your mass numbers add up. 14 equals 0 plus 14. 238 equals 4 plus 234. And so if we're trying to predict what the products are going to be of these nuclear reactions, all you need to know is what type of particle does it give off, and then you can fill in the rest of it. And so that's one of the ways that you're going to be tested on this, on the final exam. So I'll say something like uranium-238 goes through an alpha particle decay. What's the product? Or write the reaction out. And I'm just looking for you to write this to fill in the rest of it. Occasionally, something even weirder happens. So this is already kind of weird, way different than all the chemistry we've been doing so far, right? Sometimes you wind up with something that looks like an electron, but with a positive charge. Think of it like taking that neutron and shaking it until, I guess, taking a proton and shaking the proton until the charge flies off, but the mass stays the same. So it's basically an identical process, except that your particle that flies out of it has a +1 charge, but still has a mass of 0. Right? So they call that a positron. A positron is basically an electron with a positive charge instead of a negative charge, which doesn't make any sense. That's not the way matter normally behaves. It is the way that antimatter behaves. So antimatter is not just a plot point in sci-fi. It's a real thing. Antimatter exists. Antimatter is regular matter, but the charge is flipped. So an antiproton has a mass of 1, just like a proton, except it has a -1 charge instead of a +1 charge. A positron is also called an anti-electron. An anti-electron is just an electron with a positive charge instead of a negative charge. Sometimes you wind up with a nucleus that's unstable, and the way to make it more stable is if you took a proton and turned it into a neutron. And that's effectively what's happening here, is you're giving away a positron, flinging a positron off into space, and you're converting one of your protons. We're missing one proton here. When we go from phosphorus 30 to silicon 30, we lost a proton, but our mass is the same before and after. We can actually measure this process. You can actually capture these positrons from these reactions. So this is not just like something we're making up to make the numbers balance. We actually can observe positively charged electrons. All right, that sounds weird, right? Usually somebody has a question or second guesses me on this one at some point. Zach? Basically, the charges in matter are somewhat arbitrary. In our galaxy, in our solar system, protons have a positive charge, electrons have a negative charge. But that's kind of just semantics, right? It all came from Ben Franklin rubbing, silk on rabbit fur and saying that the charge that's left on this one is positive and that one's negative. Turns out those charges, if you flip those charges, matter behaves the exact same way as antimatter. If you flip the charges, all of our laws for quantum mechanics still apply. Positrons still have to follow the same rules for quantum mechanics as electrons do. It's just that the charges are flipped, but you still have positives are attracted to negatives, and you still have orbitals and electron configurations, and everything works the same way. So in our galaxy, matter is what we define as a proton with a positive and electrons have a negative. In other galaxies, those might be flipped. And there are likely other galaxies in our universe where the roles of matter and antimatter are flipped. Good question. Like, it's kind of arbitrary, it's kind of random, because at the beginning of everything, at the Big Bang, a coin was flipped, so to speak, and our universe went one way, other universes went the other way. And in theory, you could also make the argument that the amount of matter and the amount of antimatter should be equal. Because if you put everything back together again, it would add up to 0 then. So, but we don't have any way of measuring that because all those other galaxies, we can't use any of our normal tricks to figure out what those other galaxies are made out of because they interact the same way. They have the same light that we do, right? Anti-hydrogen gives off the same emission spectrum that regular hydrogen does. And since we can't go to those other galaxies and actually take a sample and measure it to confirm because we can't get there, we have no way of knowing which galaxies might be matter versus antimatter. Because what happens to antimatter when it comes into contact with matter is they basically cancel each other out and disappear. So when you generate a positron, it flies off into space. If it runs into an electron, positron runs into the electron, and they both disappear. Like they don't exist anymore. It's converted, that matter is converted into pure energy. So it's really, really energy rich reaction, but it also means it's really hard to keep antimatter in a galaxy that's primarily matter. You can't really have both of them present at the same time because then they would just disappear. Asen?
So we wouldn't be able to go to like the other.
Exactly. If we had a way to communicate with another intelligent species that evolved into in an antimatter galaxy, there might be some way we could communicate, like, oh, how do charges work there, to talk about it, but we would not be able to actually physically measure those unless we had some way of getting a small sample. We can actually make more than antimatter than just this. They were able to make something like 1/10 of a gram of antiprotons in Berkeley a few years ago. And they were able to they used magnetic fields in a vacuum chamber to keep it from running into any other matter. And they were able to let it exist. I think it existed for almost a second. So relatively long in terms of particle physics. Exactly. They published some good articles about it, and that was a big deal. But they weren't really able to do anything more with that. Daisy? Well, here's one way. I actually don't know how they did it. I just remember seeing that article. And I tried reading it, and I'm not a particle physicist, so it lost me pretty quickly. Well, basically you shake it till a charge falls off. You take a positron and you expose it to a neutron, you can get the neutron to turn into a proton. But so they had to get clever with it. They used a lot of really, really strong electromagnets and charges to keep it isolated. And they were if I'm remembering correctly, it's because they used the idea of Hawking radiation and really strong magnetic fields. Technically, everything is constantly creating these sort of paired particles. Like empty space has what's called 0-point energy in it. And that 0-point energy is basically energy that comes about because out of nothing, you can create matter and antimatter. They just, odds are, normally they immediately run back together and disappear. But if you do that in the presence of a strong enough magnetic field, you can get the matter and the antimatter to separate from each other. And so so it's called Hawking radiation because Stephen Hawking theorized that this happens around a black hole. That around the surface of a black hole, when these paired particles generate, there's a distinct chance that one of them goes into the black hole and the other one doesn't. And so that you should see these sort of charged particles around the surface of a black hole as a result of this process of matter being created and destroyed constantly. I believe that that's what they did, is they were able to capture some of this particle creation happening and use exceptionally strong magnetic fields to separate them before they had a chance to run into each other and destroy each other. But technically, constantly, everywhere, there are tiny particles generating and being destroyed because you generate matter and antimatter and then they run back together and destroy each other and disappear. Usually that's happening at such a small scale, we don't notice it. Leonora?
Destroyed, where does it, like, where does this, wow, where does the space-time go?
So we're gonna get into this in a few minutes, but now's as good a time as any. Turns out matter is just another form of energy. So this is actually not what Einstein won his Nobel Prize for, but it is the equation he's best known for. What is Einstein's famous equation? E equals mc squared. What that's really saying, energy is equal to mass times speed of light squared. In chemistry, because we're talking about reactions a lot, I prefer to put a delta. Change in energy is equal to change in mass times speed of light squared. Basically, matter is energy, and you can convert back and forth between them without breaking law of conservation of energy, because matter is just another form of energy.
What units is the energy?
So mass is going to be in kilograms. Speed of light is going to be in meters per second. So you get kilograms times meters per second squared, which is our definition of a joule. So you actually get, if you put mass in kilograms and speed of light in meters per second, you get an answer in joules. So if we did something like, so if we had, say, a positron plus an electron reacting together to make nothing plus energy, we can actually plug in what the mass is of an electron, and the mass of a positron is the same. We can plug that in for m, multiply it by the speed of light squared, and we actually get an energy for it. So matter and antimatter reacting to give us nothing but energy, we can calculate that. And that also means that that reaction can happen backwards. From nothing, you can create matter and antimatter. It's just they usually happen to bump back into each other right away because they happen to be created in the same place. Right, and so we'll do more practice with this in a minute, but basically this is one of the key aspects of nuclear reactions that makes them so energy rich. Is it turns out that that strong and weak magnetic force, strong and weak nuclear force that hold these nuclei together in the first place, they actually take some of the mass of the protons and the neutrons and they convert it into binding energy to keep the whole thing stuck together. And when you take these nuclei and you break them apart, you release some of that nuclear binding energy. And it turns out that the pieces, if you look at this reaction, if you look at the mass with enough sig figs, if you look at the mass of phosphorus 30, it's not the same as the mass of silicon 30 plus an electron. It turns out that they have a difference in mass between products and reactants in a nuclear reaction. And if you take that difference in mass and you plug it in here, you can figure out how much energy is given off per mole. All right, so these are our last two types. Like I said, we're going to do the math with it here. Maybe not today, on Wednesday. But these are our last two types of radiation we're going to talk about. If you give off a positron, we basically took a proton and converted it into a neutron. So the mass of the nucleus doesn't change. And the total number of positive charges doesn't change. 14 plus 1 still gives us 15 positive particles. Just one of them got shaken out of the nucleus as a positron. And there's the other thing that can happen is you can actually wind up with nuclei, like I mentioned before, kind of absorbing an electron. And it has the same net effect. If you basically lodge an electron into a nucleus, it basically sticks to a proton and turns that proton into a neutron. Right, and so this all winds up being, you can explain all this if you get into theoretical physics, talking about quarks. It turns out that protons and neutrons are each made of 3 quarks. And if you flip, it's kind of like flipping the spin on an electron. If you flip the flavors of one of the quarks, you can turn it from being a neutron to a proton. But that winds up generating a positron or an electron sometimes. Right, so that's all beyond this class though. For this class, we just want to be able to write out the reactions for these 4 processes. If I say there's an something goes through an alpha particle decay, I want you to be able to write that reaction out. If I say something goes through beta decay, be able to write out that reaction. And then positron and electron capture have the same net effect. In the case of the electron capture, you take an electron and it disappears and gets absorbed into a proton to turn it into a neutron. A positron does the exact opposite. A positron basically takes a positive charge away from a proton. So a proton gets converted into a neutron and you get this positron flying off into space by itself. And then the last example, that last type, that term I want you to be aware of, gamma radiation or X-ray, or just radiation in general from these, it's always just a byproduct. It doesn't actually have any mass or charge to it. It's just light. So it doesn't really get included because we can actually calculate the energy and the wavelength of the gamma radiation with this right here. So only the things that have charge and mass wind up really making playing a role in these nuclear reactions. The light that gets released is just a byproduct of these reactions because they give off so much energy so quickly. All right, so there's a we'll talk about some of this. I'm going to go fast through some of these slides. I'm going to come back to them. All right, so since we're talking about E equals mc squared, here's an example. Here's the uranium reaction. Like I said, I knew I had it on the slide in here somewhere. Uranium-235 gets bombarded by a neutron. The reactants in this case have a total mass of 236.05 grams per mole. The products, we make barium and krypton and 3 more neutrons. The products have a mass of 235.868 grams per mole. There's a difference in mass between these two. Even though it's still the same number of protons and neutrons on both sides, we add up all the protons and neutrons, it's the same. But when your protons and neutrons are present in a nucleus, the force that actually holds that nucleus together takes some of that mass and converts it to pure energy. Zach? When you add 56 and 36, you get 92. So basically, this is empirical. You can predict this if you go in and run the numbers on strong force and weak force, but it's something that it's one of those things where I won't ask you to predict this like the other types. Fission reactions, sometimes they break apart in kind of unpredictable ways. So uranium-235, when it gets hit with a neutron, goes through this process. If you hit radon with a neutron to do something similar, it would break apart in a totally different pattern. So it's somewhat random. Random's the wrong word, but it's past what we're looking at. It has too many variables for us to worry about for right now. Does that make sense? Exactly. The difference in mass between the products and the reactants is what you plug in right here. that difference in mass is what holds the nucleus together. And when you go from one big unstable nucleus to several smaller nuclei, you wind up releasing some of that energy. It doesn't take as much energy to hold these pieces together as it did to hold the uranium together. And so that energy gets released. Easy? Yeah. We'll talk about the practice test. You'll work on the practice test tomorrow. And you'll have a better idea of how to do it. So I'm not gonna have you memorize. All right. We learned how to do calculations in math with this on Wednesday and Friday. And that's our last new material for the class.
Okay.
How do I figure out to convert PSI